This video is a quick review of AP Physics C Kinematics. We're going to basically look at some of the calculus aspects of kinematics and then perhaps some experimental situations at the end. Okay, so prior to our understanding of calculus, our acceleration was always a constant value. We'll call it A. Okay, and so velocity is the integral of acceleration over time. So if I integrate this constant a, I basically end up with this v equals at plus c. Solving for those initial conditions, I basically end up with my velocity is equal to this at plus v sub 0. Integrating again gives me position, okay, because position is the integral of velocity over time, or the second integral of acceleration. So integrating at plus v sub 0 gives me this new formula, x is equal to 1/2 at squared plus my v sub 0 plus another constant c. And solving for that initial condition, again, I end up with our position equation, 1/2 at squared plus vt. Okay, and so if I wanted to go the other way, you just need to remember that velocity is the derivative of position over time. You know, don't forget that that's also a slope if I actually have an actual graph. And acceleration would be the derivative of velocity over time. Okay, with calculus, my acceleration doesn't need to be constant because I can integrate almost any function. Okay, and in real life, force and subsequently acceleration aren't going to be constant. So if my acceleration is some other formula, usually it'll be a polynomial of some sort, okay, or a monomial. Okay, so if in my example here, if a is equal to some constant at squared, I can integrate that and get new equations for velocity and position. Okay, don't forget, I left off the vector symbols in this case, but acceleration could still be a vector. The constant a could be a vector symbol. Experimentally speaking, how do I figure out these variables? Okay, most of the experiments involving kinematics require you to measure position at fixed intervals of time. Okay, every second, every 10th of a second, every 60th of a second. Our ticker tape timers, remember, were 1/60th of a second. It would measure a dot. Okay, even our ultrasonic timers measured it at fixed intervals of time. I could measure time instead. All I need to do is have a position divided by time. Is really all I need to do. Okay, and then velocity in that case would be simply calculated by calculating delta y over delta t using adjacent data points. Okay, understand that this is only an average velocity between those two time points. The accuracy can be very poor, especially if my two time points are very large separation. Okay, the smaller your delta t gets, the better. Remember, that's also something we get from calculus. As delta t approaches 0, it becomes this true derivative. Acceleration I can calculate using delta v over delta t, again, using adjacent velocity data points. Okay, but again, only an average acceleration. So you do need to be a little bit careful about that. If I know what my acceleration, if my acceleration is constant, I can go ahead and use the standard 4 formulas that we've always done to calculate a better value for acceleration, as long as my acceleration is constant. So here's an example problem. It's a little bit tricky. There's no real calculus associated with this, but why don't you try this and pause the video here, because I'm going to give you hints if you get stuck. So pause the video. Okay, if you're getting stuck here, okay, you need to understand that when the ball falls, okay, part A, the velocity of the ball just after it first bounces off the plane. Since the ball bounces elastically off the plane at point P1, elastically, remember, means I conserve my kinetic energy. So effectively, I have the same speed after the bounce as I do before the bounce. And I can calculate the speed before the bounce using conservation of energy. In part B, remember, time after it bounces off horizontally. It says there in the third line, at 45 degrees to the horizontal, as shown above. And so as it bounces, if it started out falling vertically, after it bounces, because angle in equals angle out, same as with our optics, the angle out is going to be horizontal. So this is now has become a horizontal projectile. So the time the ball is in flight is basically going to be when my x position equals my y position. Okay, distance L, as long as I know x and y, it becomes perpendicular, a Pythagorean sum. And the speed of the ball just before it strikes the plane at P2, remember, I have a horizontal velocity that never changed, but now I gained an extra vertical velocity. So try those before looking at the answers. Thank you.